We're going to move into the dot diagram section. In the dot diagram section, this is stuff we've done recently. So I'm going to walk you through these blanks. So you're going to fill them in, you're going to draw the dot diagram as you answer the questions. For the dot diagram of SO2, you got sulfur, which has 6 valence electrons. You got oxygen, which has 6, but there are 2 oxygens. Remember, we're talking about valence electrons now, not about charges, not about weights. We're talking about valence electrons. So the total will be 18 valence electrons. When drawing the skeleton structure, the element closest to the center of the periodic table would be sulfur. So we put sulfur in the middle. So the element closest to the middle is sulfur. Now we draw our skeleton structure. Put the sulfur in the middle, put the oxygens on the outside. And you subtract 2 electrons per bond from the total number of valence electrons. So I had 18, but now I'm going to take away 4 because there are 2 bonds here, one here, one here. 18 minus 4 is 14. So I have 14 dots to distribute. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm going to pause for a second. Notice that there were 2 on the oxygen from this line right here. That's 2 right there. And I needed to have on the oxygen 8, so I put in 6 more. Over here there were 4 on the sulfur, but it needs 8 also, so I put in 4 more. There were 4 there already. I put in 4 more. So now I have used, of these 14, I've used 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I have 4 left to put in. So I could put 2 here and 2 here, but I would still need 2 more there. So what I have to do is find this out. So you should find that you did not have enough electrons to put 8 electrons around all the atoms. In fact, you should be 2 electrons short. Were we 2 electrons short? I think we were. Right here, we needed 2 more. What do I do? So if you're 2 short, you add a double bond on either side to begin the process again. So we're going to put in a double bond. Now we have, in this case, I need to subtract 6 because there's 3 bonds, so I'm taking away 6. And we're going to take, when we subtract 6 from the total, that gives me 12 to distribute because 18 minus 6 is 12 this time. And I want to have 8 electrons around everything. All right, so I'm going to put in 1, 2, 3, 4, and that makes enough electrons around the oxygen because with my revised structure, there were 2 here and 2 here, which made 4. So 2, 4, 6, 8. Around the sulfur right now, we've got 6. Need 2 more. That makes 8. Then around this oxygen, there are 2 from the bond. And then 1, 2, 3, 4, 5, 6 would make the 8 electrons that oxygen needs. So if I did this correctly, how many dots will be there by themselves? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Looks like we have 12, and that should be right. All right. Now what we're going to do is look at this chart that we were given in class, or the one that's at the back, on the back side of your final review. So we're looking for domains. Domains are regions where the electrons are living. Now you're going to have to look at the actual chart that you have on the back side of your final review for this. So I'm going to talk through it, but you're going to have to follow on your chart. All right, so how many domains are there around this atom of sulfur? Okay, up here we got, looks like there's 1 domain here. So I'm going to circle the domains. There's 1, 2, 3 around the sulfur. Okay, it looks like there are 3 domains then. So that is called a trigonal planar. And that is on the sheet again on the back side of your chart. Oops, misspelled that, planar. Okay, so the electron geometry based on 3 domains is called trigonal planar. That's an AL. I'm afraid I was going to do that. So I'm just going to erase this and write that again neatly. So here we go. All right, good enough. All right, so we're going to call this, I'll write it out here, got a little more room, trigonal planar. It means it's a triangle in a plane. All right, now the name of the molecular geometry, since there are no lone pairs, up here there's, oh wait a minute, there's a lone pair. This molecular geometry, there's one lone pair, so there's a lone pair, that's this guy. Lone pair around the center atom, and two shared pairs. That means that the molecular geometry is going to be called bent. Look at your chart to follow along. And still using the table, the angles will be 120. Now, I'm not going to make you know electronegativity differences on the final, but this tells you about electronegativity differences. If the electronegativity difference is between 0 and 0.2, then we're talking about a non-polar bond. And you'd have to look up the number and do the subtraction. It's pretty easy. The difference between 0.2 and 1.7, then that's a polar bond, meaning the electrons are shared unequally. Now, if the electrons are shared unevenly, that would mean that the bond is going to have a negative end and a positive end. The end that has more electrons on it will be negative. All right, so in this case, oxygen is more electronegative than sulfur, so this end down here has a partial negative charge, as does this one, and this is positive in the center. But in reality, the molecule will be bent because of this unshared pair pushing on these guys, which causes this end of the molecule to be negative and not to be positive. So it acts like one of those asymmetrical molecules that are like little magnets that stick together to some extent. They stick to each other. Okay, so the actual electronegativity between S and O is somewhere around 1, which falls into the polar range. And once again, I'm not going to actually have you subtract them on the final, but that's how this process works. We've already talked about this, and which is a more electronegative element. That I would expect you to know is oxygen. The reason I expect you to know that is first semester we learned that electronegativity increases as you move up and to the right. So that's a greater electronegativity. All right, so which is the negative end? That'd be the oxygen, because that's where the electrons go. So if you draw this molecule and put the arrows in, here's the molecule again, let's draw it right here. It's bent like this. The arrows are going to go this way and this way, because oxygen is more electronegative. So do these arrows look like they would cancel each other out? Answer would be no. You'd get a resultant vector in that direction, so this molecule would be polar. So the answer was no, they do not cancel, so the bond is polar. Just to show you another example, if you have C double bond O like this, where it's straight like carbon dioxide, these arrows do cancel out, and so that molecule would be non-polar. All right, CI4. It's going to test me to squeeze this dot diagram in here, but there it is. C goes in the middle because it's closer to the middle of the table. Okay, you're going to have 4. 7 times 4 is 28, so you got 32 valence electrons. So you got 8 in the picture, 2, 4, 6, 8. Each bond counts as 2, so now put the other dots in. You're going to have 24 dots to put in, so each iodine gets 6, which makes 8 around all of them because all the iodines already had 2 with this bond. Okay, so the 3D structure is going to look more like this in 3 dimensions. It makes a little tetrahedral thing. Remember the little triangle base? All right, domains around the center 4. The electron domain geometry then would be tetrahedral. The molecular geometry is also tetrahedral because there are no lone pairs. Once again, this is on the chart on the back side of your sheet. Final review guide. Bond angles would be 109.5. Once again off the sheet. Since carbon and iodine are fairly far apart, we'd say these bonds are polar. Once again, you're not going to have to really worry about this. Is the molecule symmetrical or asymmetrical? Looks like it's symmetrical. So if it's symmetrical, it is non-polar. Symmetrical. Okay, SeO2. This is our structure, SeO. You're going to have a double bond. When you actually get into it, you'll find that you need a double bond to make that one work. So I'm just going to show it to you. It's going to end up looking like this, because when you do it the first time, you're going to be 2 electrons short. 3 dimensions, something like this. Okay, domains around the center, 1, 2, 3. So it's trigonal planar and bent, like the SO2 was we did earlier. Bond angles be approximately 120 since it's in a plane and you're dividing into third. The type of bond would be polar because of the Se and the O electronegativity difference. O is more electronegative, and the molecule is asymmetrical. So that means it also is going to be polar. Okay, so that's the last part of this. Last thing for the test, there will be a little section on interpreting a graph, about like the last lab we did, next to last lab, and then a little pH grid with some data about pH also. But those things you really don't study for, you just read the information and interpret. So good luck.